Okay, so good morning. I'm Elena Amato from the National Institute of Astrophysics, and I work actually right on top of this hill. I don't know if you've been uphill, yeah, so it's a nice place. I'm also a professor at the University of Florence. Yes, I mostly work on particle acceleration and propagation in several different contexts. Now, this is my first time at the school, and I have no idea of your background. So it might be that you find these lectures boring, hopefully not. In any case, I would like it to be as much interactive as possible, meaning if you have questions, doubts, just curiosities, please feel free to raise up your hand and we can discuss. Um, my lectures will be on particle acceleration, and all of them, except for this one, will actually be on the blackboard. This is an introductory lecture, and I'm using slides for this purpose. Now, how many of you have a background in cosmic ray physics? Well, okay, 5 people. I apologize if you find this boring. I'll start with introducing accelerated particles in the universe. I'll mention detection, but I'm a theorist, so it's going to be just a very quick mention. Then, during this lecture, I briefly discuss the main things we know about galactic cosmic rays, especially. And I'll discuss, of course, the supernova remnant paradigm, which is what we will have in mind when discussing particle acceleration. The generic setup that I will discuss, there are several different mechanisms by which you can accelerate particle in astrophysics, but in fact, I will focus on shock acceleration during these lectures. Um, Before concluding the lecture, I will also mention recent puzzles in cosmic ray physics that hopefully we will at least discuss briefly. And then I'll give you the course outline in terms of the following lectures. So let's start with evidence for energetic particles and extreme accelerators. The main evidences are three. We do detect cosmic rays at the Earth. We detect non-thermal radiation from astrophysical sources. And we detect diffuse non-thermal emission. All these three different observations give us information on different pieces of the puzzle. So how cosmic rays and where cosmic rays are accelerated, how they propagate, and how they propagate in different environments, meaning in the galaxy and then, out of the galaxy, and then right to us, to the Earth. The detection of cosmic rays is currently done in two main ways. We detect cosmic rays from space. We do detect cosmic rays at the Earth, but this is a more complicated measurement for low energy cosmic rays. We do detect at the Earth still the highest energy cosmic rays through their interaction with the atmosphere. The atmosphere, as we will briefly see, is a screen for cosmic rays, and it's complicated to get the particles at the Earth. Um, in terms of detection of non-thermal emission, we actually detect non-thermal emission from a variety of astrophysical sources. Here in this in this slide, I'm showing you, but I think there's too much light. No, I mean, what do you think? Yeah, it's very dark. It's can we turn off at least this closest light? Okay, maybe bad. Oh, okay. What do you think? Can you still write? I mean, okay. So in terms of non-thermal sources, the historically well-known non-thermal sources are, of course, the brightest ones and the easiest to detect. And I'm showing there supernova remnants. These are all supernova remnants of different kinds. These are supernova remnants showing mainly what is called shell emission. So you see bright non-thermal emission here as the blue and the purple stuff at the edge of the supernova remnants. And then we also have the so-called pulsar wind nebulae that are completely different kinds of remnant, where the non-thermal emission actually comes not from the outer edges of the remnant, but rather from the inner part. Here is the blue amorphous light that's non-thermal, and the same as here. And the reason is that here we're seeing a particle accelerated at an external shock produced by the expansion of the supernova ejecta in the interstellar medium, whereas here what we're seeing is particle accelerated at an internal shock, a termination shock that slows down the ultra-relativistic outflow from the central compact object, a pulsar. These are completely different kinds of plasmas and completely different kinds of accelerated particles. Here we're seeing the common plasma in the universe, electron-proton plasma, and what we're seeing is electron emission, synchrotron emission by electrons. What we're seeing here is actually an electron-positron plasma. So that's a completely, well, non-common plasma in the universe, and what we're seeing is emission, synchrotron emission, again in the X-rays from electrons and positrons produced in the pulsar magnetosphere and accelerated at the pulsar wind termination shock. What we're seeing here, this is now the jet of an AGN, an active galactic nucleus, with a black hole, with a supermassive black hole at the center. What we're seeing here, we don't know. We really don't know whether this is a common, electron-proton plasma or actually an electron-positron mostly plasma. In all cases, what we are detecting is synchrotron emission in a high magnetic field, amplified somehow magnetic field. In this case, maybe produced by the pulsar wind. In this other case, maybe amplified by the same particles that are being accelerated, as we will discuss. This issue of having magnetic fields typically higher than the ISM seems to be a necessary condition for efficient particle acceleration in astrophysics. Now, those are, well, what I was showing before are the historically known brightest astrophysical accelerators, non-thermal sources. But we're seeing now, with upgrade in all of our high energy instrumentation, an increasing number of accelerators. We're now seeing that particles are accelerated in all sorts of environment. We've known for a long time that they're accelerated to decent energies in stellar magnetospheres. We know that the sun accelerates part of the cosmic rays that we detect at the Earth. We've now also seen acceleration of particles in planetary magnetospheres. In protostellar jets, these are recent measurements of particles accelerated up to TeV energies in protostellar jets. We see particle acceleration up to, again, TeV energies, at least in novae explosion, a downsized version of supernovae. We have seen particle acceleration allegedly up to PeV energies in microquasars, which are the galactic analogous of the AGNI that I was showing in the previous slides. So this is a supermassive black hole that's doing that jet. This is a stellar mass likely black hole that's accreting and again producing an outflow. And again, we don't know the composition of the outflow, whether it is electron positive. We do know that there are protons at some level, but we don't know what's the dominant component in numbers of the outflow. We've seen particle acceleration up to possibly at least tens of PeV, possibly PeV, from star-forming regions. A neat example is which is what you see here, is the Cygnus region. Again, here we have the star cluster. We have, this is a cluster of young massive stars that have winds, and we are not really sure due to the poorer resolution of very and ultra high energy instrumentation what's doing the acceleration. We have a number of sources, including pulsar wind nebulae, the winds of the stars, possibly the collective winds that formed by the merging of all the stellar winds. So it's not clear, but we do see PV radiations from the sources. And finally, pulsars. Pulsars can accelerate particles up to very high energies in their magnetospheres, and highly magnetized pulsars, also known as magnetars, can accelerate particles in principle up to ultra high energies. So they could even be responsible of the highest energy particles detected. And as I was mentioning in the previous slides, in addition to the pulsar itself, we also have the termination shock of the pulsar wind to produce ultra PeV particles in pulsar wind nebulae. I think these are all the sources that have been potentially invoked to accelerate cosmic rays of all energies. I hope I'm not missing anything. Diffuse radiation, okay? So in that case, we were seeing radiation, non-thermal radiation from sources. We knew there were accelerated particles in the sources. Diffuse radiation is telling us, well, the combination of two things. How in the galaxies the magnetic field is distributed, up to what height above the galactic disk. Cosmic rays can efficiently emit. What we see here is radio emission, diffuse radio emission, which means synchrotron radiation, and it's telling us a combination of, how extended the galactic magnetic field is and how particles propagate in the galaxy. At higher energies, at gamma ray energies, this is the diffuse emission in, this is the Fermi map of the galaxy. We do see mostly inverse Compton radiation and photopion production. Interaction between, actually photopion and PP, in interaction of protons with photons and matter in the galaxy. You are always familiar, I guess, with non-thermal processes as synchrotron, inverse Compton, PP, P gamma. I don't have to tell you anything, right? Okay, good. The recent news is that now all these backgrounds have been detected, all this diffuse emission has been detected up to PeV energies by this Chinese experiment called LASO, who provided the first map of the galaxy at energies above 100 TeV. Cosmic rays detected at the Earth. Okay, we mentioned non-thermal radiation from the sources, diffuse emission, cosmic rays detected at the Earth. Well, this story goes back to the end of the 1800s, when there was this famous mystery of the discharge of the electroscopes. What is an electroscope? I guess you all know. It's an instrument that's able to detect charges, mostly. So the game you can play is you can charge an electroscope by just some non-conducting material that you previously charged, for example, by just this is the game that we used to play in schools with the pen. You you scrub your woolen shirt with the pen, and then the pen gets charged, and if you touch the electroscope that's made of metallic a metallic what? A metallic thing on which you have like two golden leaf, very light leaves of gold. You transfer effectively the charge, typically positive charge, to the golden leaves, and the golden leaves, of course, being charged with the same charge, they just move apart one from the other. And in principle, if there is nothing interacting with the golden leaves, they should keep their charge forever and be parted forever, but this doesn't happen. And why doesn't this happen? The initial answer to this question was, well, maybe it's, radioactivity, which is everywhere on Earth. But the thing is that and those were actually the right here when the radioactivity was discovered. But the thing is that some kind of ionization, some kind of charge transfer was occurring in the electroscope, even when the electroscope was screened from the outside by a thick layer of lead, or in a water-filled cavity. So this, the radiation responsible for the discharge of the electroscope had to be highly penetrating radiation. And one possibility, of course, if this was happening all over the surface of the Earth, so one possibility was that, one question was, is this a highly penetrating radiation coming from the Earth, or is it coming from the sky? And actually, two different scientists tried to find an answer to this question with two completely different approaches. The Italian Domenico Pacini thought that a good way to sort the question out was to go deep into the water. So if you are less exposed to this highly penetrating radiation deep in the sea depth, this must come from the sky. Victor Hess thought, well, let's go into the sky and see whether this penetrating radiation becomes more intense. Both scientists actually found the same result, that this radiation was becoming more intense going up and less intense going down the water. But this guy here was almost completely forgotten, Domenico Pacini, whereas Victor Hess, thanks to this famous discovery that the penetrating, that the radiation, the ionizing radiation was increasing, going up with a balloon in the atmosphere. Victor Hess, thanks to this discovery, got the Nobel Prize. Domenico Pacini has only been rediscovered in recent years, and now actually I think his merits are widely recognized. The name cosmic rays was actually due not to Hess, but to Robert Millikan, who thought that this radiation was actually, well, as he called it, the birth cry of nascent stars. So he thought that this radiation that at the time was recognized to have energies up to MeV was the beginning of nuclear reaction in stars being birthed. So he thought they were photons. A completely different take of the subject was that of Arthur Compton, who thought these were particles, not photons. And a juicy story is the fight that they had on a Christmas Eve that ended up on, popular newspapers, because they were actually fighting physically on this subject at a party. in the following steps in our understanding of cosmic rays have to do with increasing energy. And Bruno Rossi, for the first time, had found evidence of GeV energies in cosmic rays. At this point, the stars are sort of ruled out because nuclear reactions usually provide MEV energies not up to GeV. But the final proof that these were actually particles rather than photons came from the detection of the east-west effect. Bruno Rossi was the first, to my knowledge, to think of using the Earth magnetosphere, the Earth magnetic field to clarify the nature of cosmic rays. So the Earth has a dipolar magnetic field, and we know that particles in a magnetic field start to gyrate. So what happens is that an incoming particle coming towards the Earth, if it is positively charged, what will it do? Due to Lorentz force, it will experience a V cross B that deflects it to the east, right? Because the gyration axis of the Earth is aligned, is almost aligned with the magnetic axis of the Earth. So the idea was to detect whether most of the particles were coming from the west or from the east. The measurements needs to be done at decently low latitudes to provide an interesting result, a detectable difference in the flux of particles from the west and from the east. And when this was done, it was immediately clear that most cosmic rays are actually positively charged particles. Of course, the other important dependence that's induced on charged particles by the magnetic field is an intensity that changes with geomagnetic latitude. The magnetic field is almost, is perpendicular to the normal to the Earth's surface at the magnetic equator. So you expect the greatest deflection at the magnetic equator at the lowest amount of particles reaching you. So if you see that particles reach you more easily from higher latitudes and their flux is suppressed at lower latitudes, again, this proves that these are charged particles. It doesn't tell you much about the sign. You need the east-west effect to learn about the sign, but about the nature of the particles, this is the strongest proof. And of course, this is exactly the reason why the fact that particles reach us more easily sliding along magnetic field lines at polar latitudes is the reason why we do detect northern lights and aurora. Next steps for a long time, cosmic rays were actually also a way in which we're detecting new particles, because these were the highest energy particles available, and to detect new particles you need to go to high energies. And instrumental to this purpose of detecting new particles were for a long time what the so-called cloud chambers that I think you've all seen. And by the way, we have one upstairs, and if you're interested and you've never seen one, it could be nice to come up to the observatory. We can organize a visit to our cosmic rays facilities. We have a cloud chamber and also a spark chamber in which you see cosmic rays producing sparks. So if you're interested, we can organize one of these afternoons, for example, during professor office hours and stuff, to our facilities. Okay, so first particles to be discovered was the positron by Carl Anderson, who got the Nobel Prize for this discovery in 1936. And of course, how do you discover a positron? That's an electron that moves the wrong way, okay? The track looks exactly like that of an electron, but it seems to be moving back in time for a given magnetic field. Yeah, this was an inversion of the two slides. Um, so the discovery of the positrons dates back to 1932. In 1934, Bruno Rossi, with a coincidence system, detects for the first time extensive showers, as I was saying, at energies larger than 1 GeV. And 3 years later, Anderson and Neddermeyer discovered the muon with this impressive experimental apparatus. Then between 38 and 39, Auger detects the first extensive Earth showers, proving energies larger than 10 to the 13, 10 to the 14 electron volt, which is what is today the LHC, center of mass energy. This is just to say that those at the time were really, you know, the highest energies that man could experiment. So no wonder that you find new particles. In 1947, Powell, Lattes, and Occhialini discover the pion. And this, I think, is the last particle discovered in cosmic rays. From that time on, essentially, the game in terms of experimental cosmic ray physics was to reach higher and higher energies and better understand the composition. The detection of 10 to the 20 electron volt particles dates back to 1960. And at that point, you already know that you have subatomic particles with macroscopic energies, because if you think of it, 10 to the 20 electron volt is the energy, is the kinetic energy of 1 kilogram, a block of 1 kilogram falling from a 1 meter height. So this is, you know, a proton or an iron nucleus that has an energy that's macroscopic for all standards. Okay, why do we still worry about cosmic rays? Well, these stay, even today, the highest energies we can probe in nature. These are energies that are much larger than the 10 to the 17 electron volt that the LHC can provide. Okay, at least 3 orders of magnitude larger. And of course, this is important because you know, reaching high energies leads you to experience physics that is you know, finer and finer scales towards the unknown, towards the field where great unification theories are expected to live, and all sorts of unknown particle physics. In terms of astrophysics, they're also extremely important. And the reason why they're important is that they have an energy density which is dynamically important, meaning that this 0.5 electron volt per cubic centimeter are comparable with the energy density of thermal radiation in the universe, of thermal particles in the universe, so the pressure that the interstellar medium has. It's comparable with the energy density of the cosmic microwave background, and it's comparable with the energy density of magnetic field in the galaxy. So these are bound to be dynamically important for all the processes, for all the evolutionary processes that occur in the galaxy. Now, in this plot here, I was showing the cosmic ray spectrum. you immediately see that this is, to a very good approximation, a powerless spectrum, typical of, the typical non-thermal spectrum. Most of the energy clearly is carried by the lowest energy particles, because the power law is e to the minus 2.7 right here before the first break, and steepens after this break to e to the minus 3.1, about e to the minus 3.1. To have further changes of slope at higher energies, which we will discuss in a minute. As I was saying, most of the energy is carried by the lowest energy particles. And the maybe most interesting part of the story relies on this ultra high energy particles, and the fluxes are hugely different between the two extremes of the spectrum. The spectrum extends from, say, 10 to the 8 electron volt to above 10 to the 20. So we're experiencing 12 orders of magnitude. And with such a steep slope, about e to the minus 3, you can imagine that the flux really changes a lot between the lowest and the highest energies. And this implies that the kind of experiments that we can envision to measure these fluxes must be widely different. Here, the flux is 1 particle per square meters per second. Where the first change of slope occurs in the all particle spectrum, the flux becomes 1 particle per square meter per year. At the ankle, well, around 10 to the 18, the particles are 1 per kilometer squared per year, and here they are 1 per kilometer squared per century. So it's clear that the detectors must have very different characteristics, because you cannot wait a century to detect 1 particle in a kilometer square detector. So here, usually in this part of the spectrum below the need, you can afford detector surfaces that are sufficient for direct measurements. Here, at the highest energies, you need indirect measurements. You need to detect your particles through the interactions that they undergo in the atmosphere. And here comes the only plot I have on cosmic ray detection, okay? So at the lowest energies, you can detect particles. Of course, you want to go outside the atmosphere, because the atmosphere offers a screen against these particles. So you use balloons to go up in the air, or International Space Station and satellites. Here, instead, you need very, very big arrays, and usually what you do is that you cover several kilometers square of surfaces with arrays that are detecting the particles through their fluorescence radiation or their Cherenkov radiation in the atmosphere. Okay, I don't want to say much of this. I guess you've all, well, okay, this is the typical shower in the atmosphere, but I think you're all familiar with this kind of physics, right? What happens is that a particle that's incident in the atmosphere interacts with nuclei in the atmosphere, and the nucleus undergoes spallation and the production of pions and gamma rays, in addition to secondary products. And protons and high energy, well, high energy nuclei and high energy photons both actually are able to produce showers in the atmosphere, but the showers are very different. In the case of hadronic showers produced by nuclei, you have that the shower is much richer in terms of muons, and it's actually much wider in terms of angular extension. And this is how you go, and so morphology and muon content are the main uh, ways in which you can distinguish the two different kind of showers, and the way in which you see the shower is essentially fluorescence light and Cherenkov radiation produced by the secondary particles. And the largest detector we have for this kind of particles, the highest energy particles today, is actually the Pierre Auger Observatory, which looks at both the fluorescence and the Cherenkov radiation produced by the cosmic rays in the atmosphere. Now, enough for the measurements. Let's focus on on what affects the measurement of cosmic rays in the Earth. So the big question is, what makes cosmic rays? To understand what makes cosmic rays, we need to understand how they propagate from where they're accelerated to us. And the propagation is affected essentially by magnetic fields, right? Because these are charged particles. But magnetic fields are different in the different environments. So there is a part of propagation that, limiting ourselves to galactic cosmic rays, will be affected by the galactic magnetic field. The extragalactic magnetic field is also important for the highest energy particles that we think come out from outside the galaxy. But then another big effect is due to the solar neighborhood. So the solar wind screens us effectively from cosmic rays by providing sort of an electric field that pulls away the lowest energy particles. Of course, this is bound to affect particles up to some energy, which turns out to be of order 10 GeV per nucleon. And the last step, of course, is propagation in the atmosphere, which which is a mess. The effect of the solar wind on cosmic rays is clearly detected by what we call the neutron monitors at the Earth, in which you see that the flux of cosmic rays detected at the Earth is in perfect anti-correlation with the solar cycle. You know, the sun or star has a cycle of magnetic activity of duration of 11 years. And there is, during this 11 years, the magnetic activity of the sun reaches a maximum and then decreases. And the same goes for the solar wind. It is maximally powerful and then decreases. Right now, for example, we are at a time of maximum solar activity, and the flux of cosmic rays shows a clear anti-correlation. You see, when the sun is more active, which you can judge by the number of sunspots. This is the way in which we define the solar cycle. The sun is more active when we see more sunspots, and when we see more sunspots, we see fewer cosmic rays. Now, one extremely important step in terms of our understanding of cosmic rays was done around 12 years ago, I think, in 2013, when the spacecraft Voyager 1 and 2 crossed the edge of the solar wind, and we're finally measuring cosmic rays outside the sun magnetosphere and into the and into the interstellar medium, the so-called local interstellar medium. So those provided by the Voyager spacecrafts are the first measurement of the cosmic ray spectrum outside the solar wind. And what you see is how the hydrogen and helium spectrum here change from inside and outside the heliosphere. Okay, so you see This is the flux of hydrogen nuclei detected at the Earth, and this is the flux of hydrogen nuclei detected by Voyager, and that really clarifies the effect of the solar wind on cosmic rays. Galactic magnetic field. Yeah. Oh. Say again. So here we plot the flux of cosmic rays, okay? So this is the flux of cosmic rays detected at the Earth, okay? So affected by the solar wind. As I was saying, what the solar wind does, to all effect, it advects away the low enough energy particles. Above some energy, there is basically no difference, just because these particles are too energetic and the electric field in the solar wind is not enough to do anything decent to them. But at the lowest energy, at all effects, having a wind means that you have something that pushes you away. In terms of particles, means that there is an electric field that screens the inside from the particles. And so what you measure at the Earth is what you see here. What you measure with the Voyager spacecraft, so outside the heliosphere, is here. Okay, this is hydrogen and this is helium. So you effectively see the screening that's produced by the solar wind on cosmic rays. And you also see that the screening is sort of limited to this energy range, which is below 10 GeV per nucleon. Exactly. Yeah, the fact that there are no more points here, it's that Voyager could only detect up to some energies. Yes, exactly. Yeah, yeah. You're welcome. Please. Mm. No, I think no. I think there is no actual. I don't think that there is an actual delay. So if you look at here, it's the peak is almost coincident. I must say that in fact we are accumulating data now in the sense to better clarify how exactly these fluxes change with time. This is actually a very active part of cosmic ray research at the lowest energies. There are a number of results of variations even on daily scales now of the cosmic ray flux that are trying to be interpreted. It must be said that this kind of studies actually is telling you more about the solar wind than on cosmic rays, but it's important in any case. Yeah. Okay. More questions? No. Galactic magnetic fields. The galaxy is permeated by a magnetic field which is thought to be, which is tentatively measured to be, mostly aligned with the spiral arms of our galaxy. Okay. And this magnetic field, as I was mentioning, has a strength which is of orders 3 microgauss and an energy density which is comparable with that of cosmic rays. And the general idea is that there is an ordered and a turbulent component. And the turbulent component is of order, the ordered one. So ordered one means around the spiral arms and then out of the plane of the disk. And the turbulent component is comparable to, the turbulent component is comparable to the order 1 on scales that are, between, no, this is a mistake. It's not kiloparsec, 10 to 100 parsec scale, not kiloparsec scale, which wouldn't make sense. Apologies. In addition, again, there is tentative evidence that the spectrum of the turbulence in the galaxy is a Kolmogorov spectrum, meaning delta B squared that scales as k to the minus 5/3. Now, this is actually measured, the Kolmogorov scaling is measured not for magnetic fields, but actually for density perturbation. And the easiest thought is that the magnetic field energy density follows the same scaling, but this is sort of unjustified. Based on our theories of how the turbulent cascade of magnetic perturbation works, we would not expect an extended Kolmogorov spectrum, okay? But something more complicated. We'll go back to this because this is very important in terms of cosmic ray propagation, as we will see tomorrow, well, the day after, no, tomorrow actually. So we will go back to this kind of spectrum and what we expect on tomorrow on the blackboard. Okay, things that we think we've learned about cosmic rays. Okay, energy density we've already mentioned several times. Spectrum and composition. So far I was showing you the all particle spectrum, meaning putting together cosmic rays of all species. In fact, we can do better than that and separate the spectrum in individual components. Okay, now what you see here is the product. I think this plot is Carmelo's plot, right? Okay, so these are the protons, electrons and positrons. These are gamma rays for comparison, antiprotons, electrons alone, positrons alone, and that's it. So the first thing you see is that the proton component is dominant. Actually, cosmic rays are 98% protons and then heavier nuclei. The electrons and positrons are 1 in 1,000 actually of the positrons are 1 in 1,000 of the cosmic ray spectrum, and the antiprotons, so the antimatter component, which are positrons and antiprotons, are of order 1 in 1,000 of the cosmic ray particles. Spectral features. Now here in this plot here, we see more clearly the features that we were identifying tentatively in the former representation. So the spectrum at up to energies of order 10 to the 15 electron volt is a power law with slope e to the minus 2.7. This energy here, where the first steepening in the all particle spectrum occurs, is of order 10 to the 15 electron volt, and is called the knee of the cosmic ray spectrum. There is then a second knee, a further steepening at 3 times 10 to the 17 electron volt, and instead a flattening, so-called ankle, at 3 times 10 to the 18 electron volt. This region here is, the shaded region here, is where the transition from galactic to extragalactic is expected to occur. We'll discuss this in a second. Finally, there is evidence for a cutoff around 3 times 10 to the 20 electron volt. How do we interpret all these different features? Oh, well, what I forgot to mention is that the reason why you see things more clearly here than in the previous plot is that here the spectrum is multiplied by e to the 2.5. It's just the same spectrum as we were seeing before. It's just multiplied by the energy, which makes the slopes clearer. What are we, what is the interpretation of this different feature in the spectrum? So the first feature, the Ni, at 3 times 10 to the 15 electron volt, is usually interpreted to be the end of the proton spectrum in the galaxy. So that would be the maximum energy to which protons are accelerated in galactic sources, okay? The idea is that if the responsible mechanism for acceleration is shock acceleration, but this is maybe more general, the acceleration is rigidity dependent. It depends on the particle Larmor radius. And of course, a source that can accelerate protons to 3 times 10 to the 15 electron volt will accelerate a nucleus of atomic number n to n times higher energy, okay? That is the idea. So the steepening is that you are seeing nuclei accelerated in the galaxy rather. So you're seeing progressively the end of the spectrum of the different nuclei accelerated in galactic sources. Then the transition between the galactic and extragalactic cosmic rays will occur at around a few times 10 to the 18 electron volt. And this, as we will see immediately, is just the energy at which you can confine particles in the galactic magnetic field. So at energies above the one that corresponds to the Larmor radius of particles in the galactic magnetic field being exactly the size of the galaxy, then above that point, you expect extragalactic sources to contribute more and more. And finally, at 3 times 10 to the 20 electron volt, we might be seeing two different effects depending on the particles that you are looking at. If you're looking at protons, you might be seeing the so-called GZK cutoff, which is the fact that the universe has a finite size due to P gamma processes. I'll clarify this immediately. Or if you're seeing heavier particles, you might actually be looking at the maximum energy available in accelerators throughout the universe. Let's try to clarify this. Okay. First thing first. Okay, so we do see how extended is the cosmic ray halo in the galaxy. Cosmic ray halo is the space above, above the galaxy. What am I doing? Okay. The portion of the galaxy that's filled with cosmic rays, we said we see it through non-thermal radiation, okay? So we sort of know the confinement volume for cosmic rays in the galaxy by looking at non-thermal radiation. Once you know the confinement volume of cosmic rays in the galaxy, you can immediately see up to what energies, and you do know the strength of the magnetic field in the galaxy, immediately you can derive the Larmor radius up to which particles can be confined within the galaxy, right? So the condition is Larmor radius at energy E. There is no chalk here. Ah, okay. Okay. So you expect that once the Larmor radius of your particles is equal to the size of the halo, of the magnetized halo of the galaxy, Above that energy, you will not be able to confine particles in the galaxy anymore, right? So you work out this energy. Larmor radius is E divided EB. You use, for B, the estimate 3 microgauss. You immediately see what's written there, and it's useless. And it's useless for me to repeat. The transition energy turns out to be 5 times 10 to the 18 electron volts, okay? So why is this important? Well, because, of course, you increase the local flux of cosmic rays from sources in the galaxy up to an energy that corresponds to the confinement energy. Above that energy, the rest of the universe will start contribute more and more, right? Is this okay? Okay, so transition between galactic and extragalactic. We've had recent progress in determining this transition experimentally in recent years. In 2020, the Auger collaboration, remember the big experiment bound to measure ultra-high energy cosmic rays with the highest precision ever, showed clearly, this plot here is the relevant one for the transition, that essentially the phase of the anisotropy of the cosmic ray flux has a sharp change at around 3 times 10 to the 18 electron volt. 1 eV is 10 to the 18 electron volt. What does it mean? It means that while at lower energies, the flux of cosmic rays was dominated by the galactic disk, okay? So these cosmic rays were accelerated and leaving in the galaxy. At higher energies, the phase of the anisotropy shifts and points towards outside the galaxy. So this is clearly telling you that the transition is there. Okay. Auger taught us important things also about the spectrum, but especially about composition. This is the other very relevant thing. The mass composition was proved to become heavier above 10 to the 18 electron volt. The idea is that you are moving towards, heavier and heavier nuclei. In principle, you can become dominated even by iron nuclei. In fact, the composition that Auger proves seems to be intermediate. So towards nuclei of carbon, nitrogen, and oxygen, but not quite pure iron, okay? Finally, in terms of sources, there is this correlation that was proven at the time. Now I'm not sure how safe it is, but the Auger collaboration tried correlation with AGNI, pure plus starburst galaxies and starburst galaxies, and finding that the highest correlation is when you try and connect with starburst galaxies alone. Why is this important? Well, because the big question is, where are you accelerating the highest energy particles ever? Are you accelerating them in sources like we experience in the galaxy, supernova remnants, or in any case, young stuff correlated with star formation, in which case you expect, starburst galaxies or microquasars, I don't know, stellar mass objects. In that case, or let me put it differently. sources or phenomena correlated with young stars and the birth and the death of stars? Or are you accelerating them, for example, in the jets that are produced by supermassive black holes? This is why this kind of correlation is worth studying, and tentative evidence is in favor of starburst galaxies. But in the end, I think this claim was somewhat reduced, and correlation, Carmelo is the expert on this, the correlation is mostly with the distribution of matter, right? So I don't think that the claim that starburst galaxies as our favorite is still there, or is it? For sigma, okay, okay, that stays this way. Okay, now, okay. No, let me mention it. Okay, it's interesting that both the composition getting heavier and the correlation with starburst galaxies were two aspects that were predicted in scenarios invoking, for example, like magnetars are as the sources of ultra-high energy cosmic rays. So really stellar mass objects, only with extreme conditions in terms of outflow speeds and magnetic fields. Okay. Yes. So the 90 degrees is the direction of the galactic. You're looking at anisotropy, meaning if you get more cosmic rays from here or from there, right? So minus 90 here is the direction of the galactic center. So if you have that sources in the galaxies are responsible for your cosmic rays, you expect most cosmic rays to come from the general galactic center environment, okay, to have more cosmic rays from this direction here. What you see here is the phase of the anisotropy, so the direction to which, from which you get more cosmic rays as a function of energy. And what is clear is that the phase points towards the galactic center for energies between, this is PV, okay, and this is EV, 10 to the 18 electron volts. So in this range here, between 1 PV and 1 E and 3 EV, everything is consistent with most cosmic rays coming from the galactic center, from the galaxy, and then it shifts towards high above, which means that they're coming from outside the galaxy. But if you start getting, but if you're not confining the particles that you produce locally, and you're getting particles from a large fraction of the surrounding universe, you're bound to be dominated by, progressively, with increasing energy, you're bound to be dominated by the, in any case, the idea is that in the galaxy, and this we will discuss later, we don't have sources, numerous enough sources at least, let me state it this way, to produce the highest energy cosmic rays, meaning above 10 to the 18 electron volts. So we will discuss the maximum energy achievable in all the different kinds of sources, and we'll see that basically at the highest energies, the only sources that stay are magnetars. And in the galaxy, you do not expect, and magnetars for a short period of their life, stellar size sources. Of course, you can do on galaxy sizes. So getting to highest energies is a matter of the combination of essentially well, one thing, electric field times size, potential, okay? So this is now electric field. The potential is what you need. Size in galactic objects is limited, right? So if you want to go beyond some energy with finite scales, electric field, you need to go big, galaxy size. So that's the first thing. The other way in which you can win in terms of maximum energy is towards going to very large electric fields. But very large electric fields in astrophysics are a combination of these two things. The electric field is of order always, except for tiny, relatively small regions, of order v flow, the velocity typical of the ambient plasma divided by the speed of light times the magnetic field. So if you want to win on the other side, keeping small in terms of size of the accelerator, but large in terms of electric field, you really need big magnetic fields. In the galaxy, if you go and evaluate these parameters for the different kinds of sources, you see that the potential, the electric potential that's needed to accelerate ultra high energy cosmic rays is only achievable in fast rotating magnetars, so newborn magnetars, which are bound to be few. So whatever you do in terms of accelerating to the highest energies, either you limit yourselves to few objects in the galaxy, or you go to large scales and galaxy size accelerators. Okay. Okay, so I think we discussed this. Okay, ultra high energy cosmic rays. So we discussed essentially briefly the knee, the ankle, the transition galactic extragalactic, well, the transition galactic extragalactic. Let's discuss now the cutoff, the highest energy cutoff, whether this is telling us something about the accelerator or about propagation of cosmic rays. To understand this, we've got to consider that cosmic rays that propagate to us from outer galaxies have to propagate through the extragalactic background light, which has a broad spectrum extending in frequency from 10 to the, sorry, from, where did I go? Okay, from, okay, I understand my mistake now. It only took, 100 trials, but now I think I understand what I'm doing. From 10 to the 10, 10 gigahertz to 10 to 15 hertz. This is sort of the tentative spectrum of the extragalactic background light. And of course, you see the largest peak is here. 10 to the 11 hertz. And why is that important? Because protons or nuclei, when propagating through a radiation background, can undergo at least two very important processes, which is the photo pair production, so protons plus photon that goes into protons plus an electron-positron pair, and photopion production. A proton emits a photon and it changes into nuclei, protons or neutrons, and a number of pions, okay? Both processes, being multi-particle processes, have thresholds that are equivalent to 0 rest mass energy. And the thresholds are the ones I write here. For the proton pair production, the threshold is 2 times the rest mass of the electrons, which means the rest mass of the electrons plus the rest mass of the positrons divided the energy of the photons on which you interact, okay? This turns out to be this expression here, 10 to the 6th E gamma in units of electron volts to the -1. Now, the largest radiation background is, well, the unavoidable radiation background is provided by the cosmic microwave background, right? That's uniform and that's everywhere. And those are photons with energies of order 10 to the -3 electron volts. So when you input 10 to the -3 electron volts here, you find that the threshold for this process corresponds to a Lorentz factor 10 to the 9. Okay? So 10 to the 9 is exactly that 10 to the 18 electron volt where we were seeing this ankle. Okay, so one possibility is that what we are seeing there, that change of slope, is due to proton photon pair production. What is the effect of the proton photon pair production? Well, it reduces the size of the accessible universe. What does it mean? Well, you can define for each of this kind of processes a loss length, after which the proton loses part of its energy into electron-positron production, okay? How do you define the loss length? The loss length, well, you see it here. Essentially, L is equal dE dx to the -1. Wait. Okay. Sorry. Okay. It's much better now. Okay. Okay. So this is the loss length. Dx to the -1 times E. So you can also rewrite this as E divided delta E delta X. Okay. Now, E, this immediately reads MP divided to 2ME, which is the E divided delta E, okay? And then the delta X is 1 over sigma times N times C. Okay? Sorry. Where sigma is the relevant cross-section. Does it make sense? Okay? That's exactly what I'm writing there. Then you can input numbers. The cross-section for this process of pair production is 100 microbarn. So this is 100 times 10 to the -6 times 10 to the -24 centimeters squared. Okay? The number of CMB photons is of order 400 photons per cubic centimeter. If you input these numbers here, I can do it on the blackboard, but it's not very interesting. If you input these numbers here, and remember that a parsec is 3 times 10 to the 18 centimeters, you immediately find that the loss length attributed to this process is of order 1 gigaparsec. Okay? You can play the same game with the photopion production. Now, the threshold here is given by the mass of the pi rather than the mass of the electron plus protons, divided again the energy of the photon plus terms that are negligible, are usually neglected. This gives you 1.5 times 10 to the 18 E gamma in electron volts to the minus 1 in terms of Lorentz factor of the proton, okay? So what happens if you use here again 10 to the minus 3? Well, this number here becomes 10 to the 11, okay? Lorentz factor 10 to the 11 means particle energy, proton energy 10 to the 20, okay? So that's where you expect another feature, okay? How big is your universe at those, for this process at those energies above threshold? Again, you use the same kind of reasoning, and it's clear that now the only change is that here you have the mass of the pion rather than 2 times the mass of the electrons, and that the relevant cross-section is the photopion cross-section, which is a little larger, 300 microbarn rather than 100 microbarn. You input these numbers here, so basically this ratio now, rather than being 1,000, has become only a factor of 10, and you gain a 3 in the cross-section. The final result is 30 megaparsecs, so 1 over 30 of the, of the previous one. Why is this relevant? Because as soon as the size of your universe decreases, which is what's shown by this plot, you expect to have a feature in terms of a steepening in the cosmic ray spectrum or even a cutoff. Okay? So what these things should do is, well, the pair production threshold should correspond to the so-called second knee, further steepening due to this kind of losses. And the photopion production should induce a cutoff, the so-called GZK cutoff, okay? Now, we computed these thresholds for protons, okay? We use the mass of the protons explicitly. What happens if at these energies you don't have protons but heavier nuclei? Well, if you go back to the previous slide, you see it immediately. What happens is that actually the size of your universe increases again. So if rather than having protons, you have iron nuclei, that will not be a signature of the photopion production, but actually if you see a cutoff there, the interpretation is I'm seeing the end of the steam of the accelerator. I'm seeing the maximum achievable energy rather than a propagation effect. Okay? So it really, so that understanding the composition at the one of the big open questions, right? Because we do want to know what are the maximum energies achievable in accelerators in the universe. That would be telling you something about the universe, okay? So if we're seeing heavy stuff and the maximum energy, that's an information. If we're seeing protons, then we don't know what the maximum achievable energies in cosmic accelerators is. Oh, okay. This is the the discussion, the discussion I was doing about. Well, I started to do about the maximum energy achievable in an accelerator. What is the criterion? The criterion is what I was writing here, which I don't like the way it's written there. And I guess I can use this. Okay, so maximum energy achievable is Q of the particles times some voltage. Okay, this is the Emax theoretical achievable with infinite available time by any accelerator. Okay, then we will discuss how time enters this game and whether all sources that have such a large potential available can actually turn it into accelerated particles. But generally, an unavoidable condition in astrophysical environments is this one. The maximum energy achievable is Q times the typical flow speed in the accelerators times the typical magnetic field in the accelerator times the size of the accelerator. Okay? If you want to maximize this even beyond reason, which is what is often done, you assume that this is 1, the largest achievable limit. If this is 1, you can plot the sources based on what you know about their size and their typical magnetic field on such a diagram, which is called the Hilles plot, because Hilles was the first to write this criterion. It's actually now used in this version, but this version is not the correct one, meaning that it assumes V over C over the 1, okay? In general, if you want to really characterize a source, then you will have to deal with the proper speed typical of the source. But even maximizing all that you can maximize, you see here sources in terms of the maximum energy they can guarantee. And now, based on this criterion, you see if V over C is over the 1, even a sunspot can sort of reach the energy of the knee, which is not really the case. Supernova remnants can easily go beyond the knee. And at the highest energies beyond the GZK, you are left with the with sort of 3 sources: neutron stars, especially if highly magnetized neutron stars, AGNI of different kinds, and galaxy clusters. Okay. This is like extreme, okay? In fact, then if you want to understand what is the maximum energy achievable in a given accelerator, let me stress this again, you must consider what the typical flow speed you can expect in that accelerator is. And on this, we will go back slowly and quantitatively in the last lecture, I think. Okay, so what time are we expected to finish? Like in 15 minutes? In 20? Okay, I'll make it. It's not a lot of stuff. Okay, back to the galaxy. Composition below the knee and what it tells us about cosmic ray propagation. Okay, to 0th order, this is something that I've already told you. The cosmic rays are mostly protons and nuclei. In particular, the most abundant species, as you can well imagine, are protons and helium nuclei, and 1% is heavier nuclei. Then there is 2% of electrons and 1 per mil of antimatter positrons and antiprotons. The interesting thing is to go and compare the cosmic ray composition with the composition of matter, of thermal matter in the solar system. And you see that more or less the cosmic ray composition follows that of regular matter in the solar system, except for some very noticeable exceptions. And by very noticeable, I mean that there are some elements that are 1,000,000 times more abundant in cosmic rays than in ordinary matter. Which elements? Where boron and beryllium are the two most discrepant ones, I think. And more generally, all the elements that are secondary in nature. What does this mean? Boron and beryllium are very little abundant in cosmic environments. They are mainly produced throughout the universe by cosmic ray interactions with ordinary matter. When a cosmic ray nucleus impinges on ordinary matter, we've already mentioned this about the generation of showers in the atmosphere. What the ordinary nucleus, the interaction between the cosmic ray and the ordinary nucleus leads to spallation. Spallation means that a nucleus loses some potentially protons and even neutrons and becomes a different nucleus. This is how boron and beryllium, for example, are mostly produced in the universe, okay? They are not made abundantly by stars. They're produced by cosmic ray interactions with ordinary matter. Now, why am I mentioning this process? Well, because this is one of the two processes that provide us with the most important information about cosmic ray propagation. Measuring the abundance of secondary nuclei, we can learn for how long cosmic rays have been propagating through the galaxy. Why? Well, Sarah will discuss this in much more detail in the afternoon, but the general idea, which I'll sketch very briefly on the blackboard, is, so if you have n particles, it's based on the so-called leaky box model. If you have a distribution of particles and you worry how this varies with time, you can always write that the ndt is equal to some source term, q, particles injected per unit time, minus n divided tau escape. So this is the idea in which you have particles in a box in which you inject, the box is the galaxy. You inject particles at a rate q, particles per unit time, and the particles can escape with a typical escape time tau-esque, okay? Look for a steady state of this equation. The solution is n equal q times tau-esque. Q, the source term, is due to astrophysical sources for primary elements. So for primary elements, I can write that the equilibrium spectrum of primaries is Q astro times tau escape. Now, let us consider the secondary elements, which I said they're not there to be accelerated by ordinary astrophysical accelerators. What will this equation become for secondary elements? Well, the equation is the same. What changes is the source term. Q is not going to be Q astro anymore, but it's actually going to be what? N primaries divided the typical spallation time of the primary to produce that particular secondary, okay? For example, in the case of boron, we know that boron mostly comes from carbon. Life is much more complicated than this, but to zeroth order, we know that boron mostly comes from carbon. So if I go now and use this Q sec and write the equilibrium spectrum of secondaries, I'll have that n secondaries is equal q secondaries times, again, tau escape, right? But now, this q secondary is n primary divided tau spallation, yes, times tau escape, right? And if I now go and use in here the expression for n prime, so first thing I notice is that the ratio n secondary divided n primary is what? It's just tau escape divided tau spallation. Tau spallation is going to be just 1 over V, let's call it C, but it's V in reality, and hydrogen or whatever makes the interstellar medium, so usually a combination of hydrogen plus some helium, 1.4 and hydrogen, and sigma spallation. Important to notice, sigma spallation is constant with energy in a wide range of energy, and this is going to help us understanding how tau escape scales with energy. But the most important thing is that if tau spallation, namely if these quantities are all known, the ratio between secondary and primaries is a direct measurement of tau escape, or which I can sort of call also tau confinement, okay? So it gives me a direct estimate of the time that cosmic rays spend in the galaxy. And what do okay. Another way of understanding the time that cosmic rays spend in the galaxy is actually due, okay, yes, I forgot to mention one very important thing. This equation applies for stable secondaries. Stable meaning particles that do not undergo nuclear decay. There are also unstable elements, unstable secondaries, and well, the best known is beryllium, which is unstable. In fact, the boron is stable, the beryllium is unstable. And for unstable elements, actually, I can get an estimate of the confinement time in the galaxy based on the abundance of different isotopes. So the beryllium has two different isotopes. So the beryllium-7 and the beryllium-9, okay? When they are produced in the lab, beryllium-7 and beryllium-9 are produced with sort of the same abundance. When I go and measure it in cosmic rays, the abundance of beryllium-7 and beryllium-9 is different because the beryllium-9, well, actually 10, is unstable with a decay time that's known, and it's of order 1.5 mega years, okay? So when I measure in cosmic rays the different abundance of unstable versus stable isotopes, again, I can turn this into an information on the confinement time, on the time cosmic rays have spent between the sources and the Earth, okay? So both actually estimates, it is interesting, by the way, that when you measure this, an additional hint that this is a good estimate of the confinement time is that for different unstable isotopes, you sort of converge on the same kind of number. And this number here, measured for radioactive elements, actually points to residence times of order 10-15 megayear. I was mentioning before that from the boron over carbon, you get a confinement time which is sort of an order of magnitude smaller. Whatever you do, if you compare this time, 1 million year or 15 million year, we will discuss this later, with the typical propagation time through the structures in the galaxy at the speed of light, because these are relativistic particles, typical propagation speed that you expect is of order the speed of light, you see that in order to cross the galactic disk, which has a height of 300 parsec, the characteristic times is just 1 kiloyear. To cross the galactic radius with a size of order 15 kiloparsec, the time would be of order 50,000 years. To cross the galactic halo, the magnetized galactic halo with size of order a few kiloparsec, again, the time would be of order 10 kiloyears. None of these times is comparable with the millions of years that cosmic rays are bound to spend in the galaxy based on the measurements I just mentioned of stable and unstable secondaries, okay? What is this telling you? That propagation cannot be at the speed of light and cannot be on a straight line. Propagation must be much slower than that in the galaxy. Another clue in the same direction, and again quantitative, is provided by the level of anisotropy. Okay? Anisotropy is a quantity that basically measures the ratio between the cosmic ray current and the current attributed to a uniform, to an isotropic distribution of particles propagated in all directions at the speed of light. So it's this quantity here. And it is of order of V propagation divided by C, V drift divided by C. When you go and measure it, the measurements give you a number for this delta between 10 to the minus 4 and 10 to the minus 3. How can it be so low, the propagation speed with respect to the speed of light? Well, to zeroth order, in principle, you could interpret the anisotropy as simply due to an anisotropic distribution of sources. In which case, however, the anisotropy should scale as 1 over the square root of the number of sources. And this kind of small number here would give you a GeV energy is an incredibly large number of sources, just unthinkable to be in the galaxies. Of order 10 to the 8 sources you would need able to accelerate GeV cosmic rays, which is unreasonable. The other possible interpretation comes from this equality here. This magic number, 10 to the minus 3, 10 to the minus 4, is of order the ratio between the Alvan speed in the interstellar medium and the speed of light. How many of you know what the Alvan speed is? No one? Okay. So, okay, the Alvan speed, which is this quantity here, B0 divided square root of 4 pi rho ISM, density of the interstellar medium, is the typical speed of propagation of magnetic perturbation, magnetic disturbances in the interstellar medium. This is the speed that's typical of the so-called parallel hydromagnetic waves. Waves moving in the direction of the ordered magnetic field, ambient ordered magnetic field, entailing a perturbed magnetic field that's perpendicular to the propagation direction. So if I have the magnetic field along Z, these are waves that propagate along Z with accompanying magnetic field along X and Y, perturbed magnetic field along X and Y. And the important thing about Van waves is that these are stable solution of the for plasma dynamics. Okay, so these are perturbations that are not easily damped. So they can be produced and be stable over long times and length scales. So they're bound to be everywhere because of this reason. The interesting thing is that the measured degree of anisotropy is comparable with the ratio between the Alvan speed, the speed of this perturbation, and the speed of light, which immediately makes you think that maybe the cosmic rays, in fact, propagate at the speed of these perturbations. And one step forward, which we'll actually make quantitatively tomorrow, is to think that cosmic rays go at rest with a system that's moving with magnetic perturbation. They are effectively scattered maybe by magnetic perturbation so as to go at rest and isotropize in a reference frame that's moving at the speed of the scattering centers. And this is the interpretation, finally, of the cosmic ray anisotropy at these energies in the ISM. So the picture that arises is that basically cosmic rays will be produced by sources somewhere in the galactic disk, well, cosmic rays below the knee, cosmic protons below the knee, will be produced by sources somewhere in the galactic disk, and they will propagate to us, not in a straight line, but diffusively, interacting with magnetic perturbation, and finally going at rest in a system that's moving going to isotropize in a system that's moving with Alvan waves. And what is this telling you? That there is no way to track back cosmic rays to their sources because they're not pointing to their sources. They will actually move in a way that we will find to be diffusive with traveled length proportional to the square root of a diffusion coefficient times the time. So the length traveled does not increase linearly with time, but rather with the square root of time. And they will in no way point back to their sources. So the possibility of source localization is completely lost. Sources of cosmic rays. I will just mention it, and then I'm running out of time, but I'll try to at least mention it. So the sources of galactic cosmic rays were proposed very early in time, already in the 30s. Remember, the discovery of cosmic rays dates back to 1912, and the understanding that these were cosmic particles rather than photons dates back to the 30s. And already by the end, actually in the mid-30s, it was proposed that the sources of cosmic rays could be supernova explosions. Okay? The proposal was actually initially only very qualitative by Buddy and Zwicky, but then it was made quantitative, at least in terms of an energetic argument by Ginsburg in the 60s. And how does the energetic argument work? Well, the luminosity of cosmic... Oh, la Peppa. Okay. No. You said, didn't you say 55? Ah. No, okay. Yeah, okay. So only the energetic argument and the rest we will discuss tomorrow. I'm sorry. I'm always so slow. Okay, so the luminosity of cosmic rays required in the galaxy. Well, one easy way to compute it is use the volume of the galaxy as we spotted. Okay, so a halo of, say, 3 kiloparsec, a disk. So this is a cylinder with a halo of 3 kiloparsec and a radius of the disk of order 15 kiloparsec. the cosmic ray density that we mentioned of order 0.5 electron volt per cubic centimeter, and the confinement time that we learned from secondary to primary ratios or unstable secondary decay time. You go and estimate this luminosity, and you immediately get that this number is between 310 times 10 to the 40 ergs per second. You go and compare with the luminosity that's provided by supernova explosion. And this is just the, here there is something screwed up, but the rate of supernova explosion times the energy released in a supernova. And the energy released, the kinetic energy released, the only available for particle acceleration. The kinetic energy released in a supernova is 10 to the 51 ergs per second, a pretty universal number. The rate is 1 in 30 to 100 years, we think, but we're still waiting. You immediately get, yeah, I think that this is actually, yeah, okay. So you immediately get that the luminosity of supernova is a comparable number. I think that there is a mistake in these numbers. Probably this is at 10 to the 41 ergs per second. And if you go and compare the cosmic ray luminosity and the total energy released by a supernova in the per unit time, by supernova in the galaxy per unit time, you find that between 3% and 30% of this power, the typical number that's quoted is 10%, is enough to power the flux of cosmic rays. And this is what makes the argument quantitative. The Baden-Zwickis argument quantitative. We'll go back to this in the next few lectures and especially clarify how you convert, at least in principle, efficiently, the kinetic energy of a supernova in accelerated particles. Enough for today, but I'm open for questions. But maybe you want the coffee, and I'll be available for questions together with Sarah also in the afternoon.